sometimes we're going to be asked to actually calculate the energy barrier in kilojoules per mole to rotating this molecule, all right? And what we do is we are actually going to memorize 4 really common values. And by memorizing those 4 really common values of energy, we're going to be able to solve for what's called the barrier to rotation, okay? So what are these values that I'm talking about? Well, there's basically 4 really common interactions that you should commit to memory in terms of their energy level, all right? And in terms of which one's most energetic and least energetic, you should already know that based on the fact that anti is going to be the least energetic and eclipse is going to be the most energetic, all right? But we actually need to know the values for this, so let's just talk about it, all right? First of all, we have 2 eclipsed values. Notice that they say, well, actually we have 3 eclipsed values, but let's just start off with the highest one. The highest eclipsed value that you guys need to memorize would be 2 methyl groups perfectly overlapping eclipse, okay? If you have 2 methyl groups that are overlapping, that's 11 kilojoules per mole, which is a lot of energy to spend, okay? That energy that we're talking about is actually referred to as the energy cost. That basically means if I were to rotate these bonds eclipsed, how much energy would it cost me? 11 kilojoules per mole is kind of a lot, so you can imagine that that's not going to happen very often, or sometimes it's going to want to prevent that as much as possible, okay? So let's keep going down the list. So an interaction that is still not very favorable, but is a little bit easier to happen, is eclipsed with a methyl and an H, okay? This is going to be a little bit less energetic because now we don't have 2 big groups, we just have 1 big group and an H, okay? So there's obviously some torsional strain going on here, but it's not quite as bad as, as having 2 methyl groups, okay? So then we've got HH. HH, and by the way, that one is 6, so you just have to remember that one's 6. Then we've got HH. HH is the easiest one to happen for eclipse, but it still does cost some energy. So for an HH eclipse, that's going to be 4 kilojoules per mole. Again, just something that you should commit to memory. Then finally we have gauche, okay? We're not going to have to memorize all the different gauche combinations because that could take a long time. That could be very exhausting. But one that you should know is 3.8 kilojoules per mole. Now notice that this number is actually very close to 4. So how can a gauche interaction be almost the same as an eclipsed interaction? And the reason is because the gauche that we're talking about is actually methyl-methyl gauche. So this means that you have 2 large groups that are staggered, but they're so big that they're interacting in almost the same way as 2 H's would if they were overlapping, okay? These are your 4 values that you want to commit to memory because guess what? For these types of questions, they're going to give you these values, and then you're going to have to solve for the unknown bond interaction by figuring out these values.